Thank you for the possibility to speak today. And I would like to emphasize that everyone is welcome, because in the morning session I have seen that there are lots of papers or talks which are closely related to images. So whether they call it AI or something else, pattern recognition, most of the techniques are applied on images. So there is a place for those people at our conferences. Also in the summer we are organizing there are two summer schools in Hungary. One is SSIP, which is in Szeged, and the other is SSRM. So if you Google this, you will find two international summer schools with good programs with lots of speakers on these fields. So everyone is welcome. So the title of my presentation is quite generic, but naturally I will just talk about very few problems which we met during different applications of image processing in industry or related areas. So first I will tell you a few words about few-shot problems, few-shot learning. I guess everyone knows what is few-shot learning, but I will just highlight some ideas which I think is important when trying to attack such problems. Then I will have a few slides about randomized networks, then how we can utilize these simple structures on a larger scale in larger networks, how to improve their performance, and then what is the drawback of these traditional random networks and how to overcome of this. We started this research. And then in the second part I will talk about matrix learning, which we apply for peer recognition, and there one question is how to improve the performance by injecting semantic information into this image processing techniques. There's a question we try to answer. So these few words is about what is the source of the problem. So in few-shot learning we have a limited number of label data for some classes. It means maybe we have only 1, 2, or 5, or generally less than 10 shots, 10 samples of some classes. So the question is how to generalize our network to have a good performance on these new classes. We have seen today already a lecture about continuous learning, which also tries to attack this problem. But generally it's discussed in the group of few-shot learning algorithms. So these classes which appear we call unseen classes, and typically they appear after the long training of a bigger backbone, a bigger network. So the problem is we've done some work, and now comes a few problems how to deal with this, how to avoid catastrophic learning, or how to increment our model to include the new classes. So the possible solutions can be grouped into two sets. One is making new data. So we can apply data augmentation to generate additional training data. We can use classical image processing techniques, or we can use generative models such as GANs or variational autoencoders to have this new data. And the other solution for these problems is to make good models, what we call good models, which make robust generalization. So it means we need models which capture the generalized data, which is hidden somewhere, latent information, which can be applied to the new classes. So how can we do this? There are approaches which use transfer learning. The question with transfer learning, how fast it is and how efficient it is. And the other approach is meta-learning, where we try to include some meta-information, other information to increase the information content that we have about these few classes. Okay, so now going back to time. So a few months ago I had to keep a lecture about AI in image processing. So I just looked through some papers, and I learned that it's a long history of AI. So it started in the 40s, and many things were reinvented in the last 50 years ago. So many things are just reinvented. So what I found, for example, about these random networks, that the first, this idea was published in 1992, then a similar idea was published in 1994, then Huang had a paper in 2006 with lots of something like 10,000 references. So he reinvented something, but the main idea is the same. Have a shallow network At that time, we didn't talk about deep networks, which has two layers of weights. In the first layer, they have random weights, and on the second layer, they can compute these weights. So there is no need for optimization like SGD or other things. You can simply mathematically compute the weights. So the intuition comes from the biological systems, because we know that our nervous system is quite complex, and it's difficult to just imagine how it was optimized during the thousands of years. So maybe we don't have to optimize all the weights. If you have lots of connections, maybe most of the connections can be random. And some weights should be optimized, so we don't have to optimize all the weights. If we keep most of them random, the less can be probably computed or estimated in a much faster way. So that's the idea. So what are the main common properties of these networks? They have random weights. The output weights are computed by fast equation solvers. So because this is a shallow network, we don't need optimization. They have relatively good performance if you compare to similar shallow networks. So the same or sometimes better components, but they are shallow. So there's a problem, shallow. So mathematically speaking, I guess everyone is familiar with the basic equation of a single layer network. So we have the target, and if we want to estimate the target, we have the input weights multiplied by the input data. So these are denoted now by R because they can be random. And on the second layer, at the output, we have these weights which should be computed. So if we write the equation, the target equals this matrix, these random operations multiplied by W, the matrix of the weights. So we can compute, the question is the weights. It can be computed as an inverse problem, so we can compute it in the pseudo-inverse techniques, and it works for most of the cases. So we have done, and other people done, thousands of experiments, and okay, mathematically this is not very precise, but practically in a least square sense, you can get the solution in over 99%. So, okay, we have this network. How can we apply this in such bigger networks? So I will show you this through an example use case where we have to classify steel surface defects, and this is in the framework of few-shot learning. So how can we apply this in few-shot learning? So in this example, we have a data set of surface defects of metal surfaces. Here in the columns, you can see the classes. They are sometimes similar to each other. Sometimes it's easy to distinguish them. As a few-shot problem, 4 of the classes are known. So we have lots of time to train 4 classes. But 3 of the classes are unseen. So the question, if you have a network trained for 4 classes, what happens if you see a very few shots from the few classes? What is the average performance on this? For the backbone, you use one of the efficient net variations, and what we did here is to put the randomized network to the head of the structure. So the proposed two-phase training has 2 steps. In the first step, we have a big network, a traditional image processing network like efficient net. So for the 4 classes, we train this network. And on the second step, we keep one of these fully connected layers of this, but we add this randomized network, which is very fast to compute. Okay, so here are some tables, some data about the results. So in the columns you can see as the number of shots increasing. So it means in the first case we have only 1 shot of these 3 classes. In the second part you have 3 shots, 5, 10, or even 20. So if you have 20 shots, we don't call few-shot problems. So what is the performance? The performance is computed here in this test bar of F1 scores, and we give the rank from these 5 competing solutions, which is the best and which is the second one. So if we apply error technique, which is denoted by this ellipse, red ellipse, you can see that if we have a few shots, it's the first, then the second, and if we had 20 shots, then it's only the third. On the last line, you can see the solution when the whole network was optimized by the Adam optimizer. And in the second line, you can see a case when only the head was computed by the Adam optimizer. So as you can see, if we have few shots, even our results are better than the Adam optimizer. But we think that's a very good optimizer, that it had to compute only optimizing 2 layers. But with this random technique, if you have few shots, you can overcome these methods. So what is written in the papers that this randomized network has a very good generalization abilities. It's true, because if you have very few information about the new classes, this generalization ability helps. Okay, and what is the other advantage of this? The other advantage is the computation time. For these 5 solutions, you can see here the time columns. In the first line, you can see the randomized network, and if you go behind, and then the last row of columns is if you compute everything with the optimizer. So you can see it's 1 or sometimes 2 order faster. So if you have few shot problems, 1 or 2 or 3 or few new shots arrive, you can very easily reconfigure your big network with quite good performance. So the main problem with this networks is that they are shallow. So no, you cannot do anything with shallow networks, except if it's a head. If the head is typically not very deep. The first, as you know, most networks in image processing are convolutional. There are residual networks, bottlenecks, lots of things. But finally, at the last layers, typically we have something called a head, which is fully connected. So we can use it here, but how to increase the depth of this? So here we just tried a very simple idea. It's a kind of a differential evolution approach. It means in the first step we have one network, which is a random network. On the first layer you have the random weights, and the second the weights you computed. So this is an approximate solution for the problem. So if you compare it to a fully connected network with more neurons, more networks, you can say, okay, it gives something close to the best results of the other network. So we consider it as a starting point. So let's start to increase the depth of this network. We keep the original neurons, the original cells. So these were the output cells in the first phase. Or the next phase, these will be the output cells, but now they are a hidden part. They become a hidden part of a hidden layer, and you add new neurons as the output. And here you can add more neurons. These neurons the weights of these new neurons can be random somehow. They can be the perturbation of other weights, or they can be completely random. What we found best is to generate orthogonal weights, which a kind of good sampling of the parameter space. We have not just simply something random, but which just tries to sample the data from many aspects. So we made a little benchmark. So we compared this technique on 12 data sets. This is the set. The table contains this information about the data sets, and compared our network with the fully connected CNNs, fully connected networks with the Adam optimizer and other similar. I don't want to go into details. It's called the extreme learning machines, a kind of random networks, and we found from the 12 cases, in 6 cases, the best results were achieved with this network. And again, if I compare the time, the running time for the training, you see sometimes it's only just half, but sometimes 1 or even 2 order faster than running the RM optimizer on a CPU. In this test, we didn't implement a GPU or other parallelization technique. Everything is on a single thread on a CPU. Okay, so this was another solution how to attack few-shot problems with these randomized heads. And in the second part of my talk, I will talk about something completely different, but also very useful for few-shot learning. These are the class of networks which are called metric learning networks. So what we call metric learning. So these networks has the purpose to embed the input information into vectors, which can be well represented in a metric space. So typically in the loss function, there is a distance or similarity measure to evaluate the similarity of the input data according to some specific task. So when we train the embedding network, naturally, you have to define a task which somehow contains inherently the semantic information or something hidden that you want to extract, but you want to learn from the network. So, for example, in this figure, you can see an embedding of pills, of medical pills, on this 2D graph. So we did some metrics algorithm to to make the representation now projected to 2D space, and you can see the shapes and the colors of these small marks just represent the colors and the shapes of the pills. So it means if you give different types of pills, medical pills to the system, it will place them in a metric space, and if two pills are similar, more similar to each other than others, then they will be more closely represented. So the main advantage of such approaches is that they are very good in generalization. So they don't learn specific classes, but they learn what to know about the classes to be able to differentiate between them. And the other is that when you apply these techniques, you just make the embedding, and you can use simply metric comparisons of embedded data. So it's very fast to compare classes. And if there is a newcomer, an unseen class, you can just simply place them related to the other in this parameter space. So you can easily handle new classes. The few-shot learning problem is almost solved. Okay, so this is the case we were working for the company who developed this system for medical peer recognition. So it's a very good use case because we have large number of classes. Sometimes there are very small differences between the classes, and naturally it depends on the observation circumstances. Here you can see two pills in the two lines. On the first line, the two pills are exactly the same, but because of the light was a scattered light, you cannot see the embossing on the surfaces. And on the second line, you can see even the colors and the intensities greatly changes. There are reflections. Sometimes the imprints are not visible. So the pills are designed to look different, but in many normal cases, they simply don't look different. So the approach is to take a query. You have a big data sets, and also from the query and the data sets, you make the embedding with these metric networks, and then you can simply compare the metrical representation of this data. So what we made a system is, we call it a multi-stream image processing network. It means to enhance the differentiation, the ability to differentiate of the classes. We use the classical image processing techniques, like we extract the contour, we compute the texture descriptors, we use the LBP. So we extract some classical image features in the first phase, and we train also, I guess, efficient net here to make an embedding. So we train it for a metric embedding these systems, and in the second phase, we just freeze these layers, and we apply attention layers and fusion layers to fuse the information in these different phase streams. So each stream tries to solve the problem itself alone, and then we combine the results. Okay, how do we train the streams themselves? So this is a metric approach. We have three inputs. One is we call it anchor, and the other is a positive sample, which is the same class, and a negative sample, which is a different class. And we want the network, which is a Siamese network, to place them in the parameter space. So if something is the same class, it will be close to the other one. If it's a different class, it will be far. So this is achieved by this triplet loss function, which contains the distances between the positive and the anchor, and the positive, and the anchor and the negative samples. Also, there is a margin here, denoted by M, which defines how far the negative sample should be from the anchor. Okay, so we just achieved quite good results with this implementation, but the idea was how to increase the precision somehow involving semantic information. Because people generally talk about DNNs and CNNs, they are semantic, they do something semantic, because when we train them, the task is a semantic task. But here, the loss function is quite simple. Something to be close or too far to each other is, I wouldn't say exactly, it's a semantic thing. What we can get semantic information about peers is in the official description of the peers. So you can download from the internet in Hungary the description of all the peers, and in this textual paper you can find a small section which describes the morphological properties of peers. like the pharmaceutical form, the color, shape, convexity, edges, imprints, and or engravings. This is written in Hungarian language. And so we just extracted this text and used the HUN-REN News-LG large language model, which is trained on the Hungarian Web Corpus 2.0 over 9 billion words. And we make the embedding of this information. Okay, so it means by this technique, we just don't have we have some kind of real semantic information by words, how two pills are similar to each other precisely by the semantic description of them. So if we have this information, we can inject this into the matrix triplet function because it contains a variable which was denoted by m, how far they should be placed in the parameter space. So if in the description they say they're completely different, they should be placed far. So m is computed by this. Okay, and I guess the time is over. So that's why I jumped to my last slide. I just have the results here. We have different data sets, and we have our own data set, which also includes the semantic data with free text descriptions. And we just can report that by this semantic information, the classification accuracy can be slightly improved. And I don't tell you more details about how the visual semantic information can be improved with much higher, slightly higher results. So thank you for your attention. I guess this is what I had the possibility to tell you, and I thought it was important. Thank you, Csaba.
Thank you very much.